Hi all, I am Brent Soomers and it is my pleasure to introduce our CVPR2026 paper, NVGS, Neural Visibility for Occlusion Culling in 3D Gaussian Splatting. In this work, we propose a novel pipeline for rendering large, composed scenes consisting of individually trained 3DGS assets. Concretely, we examine the problem of rendering overhead and seek to minimize it by pruning primitives that do not contribute to the view. While 3DGS achieves high frame rates and high quality, it incurs pre-processing overhead for Gaussians that are not used because they are occluded. They do, however, still sort, compute color, and create buffers for such Gaussians. Given this problem, we want to minimize this overhead by pruning Gaussians before any such expensive pre-processing is needed. Given the extensive use of occlusion and backface culling in traditional meshes, we looked there for inspiration. This, however, is not trivial, because unlike triangles, Gaussians are semi-transparent and the frontmost Gaussian does not necessarily occlude the Gaussians behind it. Because Gaussians are blended front to back, it is also hard to determine which Gaussian will saturate a pixel. Our work is based on the insight that early stopping already tells us when a pixel is saturated, so by baking this information into a lightweight MLP with tiny CUDA and N, we can efficiently determine visibility before any expensive pre-processing is needed. Our method starts by extracting the contribution to a set of training views. We center the asset and remove all Gaussians with an opacity below a threshold of 1/255, as these are already ignored in the rasterizer later on. We then calculate a minimum and a maximum distance within which we will sample views based on the projected size of the asset. With this set of views, we extract contribution from the renders using the formulation proposed in Eagle and Prox. This formulation accounts for the weight applied to the color, which combines an opacity and a transmittance factor and works with changing directions and distances. We then binarize this formulation with the contribution above 0 indicating that a Gaussian was visible. As 3DGS suffers from popping, we include a small set of auxiliary views, and the final visibility to a view is the logical OR of its contributions to the main view and to this set of auxiliary views. Given the ground truth visibility labels, we train a lightweight MLP to learn these visibility functions. Concretely, we train one main visibility MLP that takes in the Gaussian mean and viewpoint information, and additionally a feature vector representing the Gaussian parameters. This feature vector is learned by a secondary MLP that takes in the original Gaussian parameters as input and outputs a 6-dimensional feature vector. We chose this architecture to ensure the inputs to the visibility MLP are a multiple of 16, as tiny CUDA and N has efficiency breakpoints at these values. We then use binary cross-entropy loss and per batch weighting to account for the number of times a Gaussian occurs in each batch. We want to emphasize that the secondary MLP needs to be run only once before rendering, after which only the visibility MLP is needed. Second, the MLP is shared across instances of an asset, so we only need to pass its weights once. During rendering, we thus need to convert the instance inputs back into training space. To do this, we undo the translation, rotation, and scaling transformations, and additionally, we apply a field of view correction factor to account for the fact that a smaller field of view creates a zoomed-in effect. This requires visibility to be selected as if the viewer were standing closer to the asset than the Euclidean distance would suggest. Think of this as looking at something through binoculars, where the physical distance to the object remains the same, yet the object is seen at a higher detail level. With these transformed input parameters, we query the MLP for visibility and cull Gaussians that do not survive frustum culling or visibility culling. We then create instances only for surviving Gaussians and drastically reduce VRAM usage. Our method allows us to prune occluded Gaussians, reducing the number of instances generated for rendering and avoiding pre-processing for invisible Gaussians. In our paper, we demonstrate that our approach drastically reduces VRAM across all scenes and improves FPS at close, medium, and far distances compared to baseline 3D Gaussian splatting. Compared to dedicated LOD approaches for composed scenes, the same observations hold up, except that LOD naturally catches up in FPS at greater distances. We also show that our method produces minimal visual differences compared to ground truth renders, thanks to our culling approach removing only Gaussians that do not contribute to the render. The MLP can be trained in a couple of minutes per asset and reused for instances that change rotation, translation, and/or scaling. Here are some videos on the benchmark scenes. And I want to thank you for listening, and if you have any questions or remarks, please don't hesitate to reach out.